Okay, so um, let's map the idea of pipeline onto the data path we've already implemented early in chapter 4. Okay, so if we put the stages mapped onto this diagram you see here, right? So here would be your instruction fetch state, right? The first stage. Then you have your ID. Then you have your execution stage. And then we have mem. Okay? So where we access memory, and finally we were supposed to write back. Okay? So if you map them on the data path pipeline that we implemented, it's going to be surrounding these sort of regions. So the way we see here, we are only able to go from left to right. So on those two instances that we are coming back right to left, except two exceptions, we're gonna have hazards. Okay, so you see, the only two exceptions are first the update of your PC, okay, that we're coming back. So this is, we send either the ALU result or the data from memory to the left, right? And the second exception that we can go from right to left is the write back stage, right? This one, which we place the result back into the register file in the middle of the data path. Okay, so excluding these two exceptions, if we go right to left, we're gonna have hazards. Other than that, we always should follow from left to right. This is the way they're prepared and sent to the next stage, from instruction fetch to instruction ID, instruction decode, and also register file read, execution, mem, and write back. Okay. Now, we also talked about putting registers into each of those in between stages so that we can hold the information which was produced in a previous cycle. So the point here is these registers shown in blue should be wide enough, right, to store all the data corresponding to the lines that go through them, right, from here, 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 and all of those. For example, for if instruction fetch and ID stage, right, the register must be 96 bit wide. So I'm just gonna put because we have 32-bit instruction fetch from memory, right, coming here. And we need to increment 64-bit PC address, okay, comes here. So that's why 32 and 64, we have 96. So different registers for each stage has its own different size that we gradually get to learn, okay? So that's the idea of putting registers in between to hold on to the information which was produced in the previous cycle. So now, let's see how we're going to use such a notion in some examples, okay? So we're gonna see cycle by cycle flow of instructions through the pipeline, okay? One in single cycle format and the other one is multi-cycle diagram. So let's see single cycle for load, okay? So the portion of the data path that was used at that specific stage, it is shown in color, in blue, okay? So we've got a load instruction, and that is the instruction fetch stage of that load, okay? When we start fetching load, right, in general, there's no confusion when reading it, right? We can read and write register at that point, so there's no issue before we start, okay? Because normally, as you recall, the content change only at the edge of the clock cycle. That was the convention we had before, okay? Although the load, right, need only the top register in stage 2, which is this, in order to be conformed to the convention, it doesn't hurt if we put extra work and we still sign extend the values that are put through this. Okay. So now this is the first stage of the load. Going forward, now we're going to have the second stage, which is the instruction decode. Okay, now only this portion of the pipeline is going to be used because the data has been passed through this register, and then it was triggered at edge of the clock. So we are in this stage. Now, what we need to do for instruction decode and read register is to understand what are the read registers are going to be used, like these two. We need to use 32 to 64 IMM jam, right? And then we're going to pass it to the next level, which is the execution phase. Okay. If using this 34 to 64, now we are doing actually the sign extended version of a register. Can anyone recall what the sign extended was? When we say sign extended, what do we mean by that?
You fill the leftmost bits from that value to the zeros and ones, depending on what sign it is. If it's positive, it's zeros, and if it's negative, then ones.
Yeah, because we are trying to widen up, extend the size of that bit value to whatever we were trying to have. Like if it was 32, we wanted to make it 64, 128, or 96, depending on the convention, right? So we take the most significant bit of whatever it was, as your colleague said, and we put the rest just like it was. Okay. All right. So now the register is added to the sign extended immediate, and then the sum we're gonna place it in XMEM pipeline register. Okay. We go to the next level, and then for the load, data memory. Let me see here. So actually, the stage has been completed when we reached this. So after the data memory is read using the address of XMEM pipeline register, okay, and then and afterward we're gonna place the data towards mem write back register. Okay, so pretty straightforward. So that was the 5 stages that a load instruction needs to follow. Now let's have a look at at the end for the write back. I mean, since for the load the write back is actually nothing can change anything in the pipeline. So what we do is we need to update this result back to this side of, right, the registers. Now, there's a bug in here. Can anyone mention what it is? Where exactly we need to update the write back result of this? So we're here, data are read from the mem write back pipeline register and written into the register file in the middle of the data path. Okay. Where exactly are we updating? Are you still here? So the correct flow is passing the right register number first to the ID or X register, right? And finally, the mem or write back register, okay? So here, 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 and then coming back, the register number during the write back stage to specify the register to be written here. So after we reach here, the 2 hops, now we know what to write back, okay? So the correct design would be passing it stage by stage and then know where to write back in the right register, okay? Also, including that register number that we need to write to, we need to have the data itself, right? So we have to pass the data with it at the same time. So we need to add 5 more bits for the register number because we have 32 in RISC-V, and also we have the data included with that to write back in the register. Okay, so that was for load. For store, up to the point of the instruction fetch and ID, it would be sort of equal. So there's no issue in that. So let's just start talking about it after reaching the ID or X stage, right? The register corresponding to that, and in the execution phase. So that's the X stage, okay? For store. Now the operation is store. So for store, unlike the third stage of the load we just saw, the second register, right? The second register value is loaded into the XMEM pipeline. Okay? Why? You seem very confused now. There are only 5 stages and a bunch of operations, okay? Load, store, branches, that's all.
Which pipeline is it in?
What is it?
You said which pipeline is it in?
Which pipeline is it?
What was the question?
So the question was, now we are dealing with a store, okay? An operation that want to store something. The second register value, okay, is loaded into XMEM pipeline, which is this. Okay? The second register value is loaded into XMEM pipeline register to be used in the next stage. Unlike the third stage that we just saw for load. What's the basic difference between load and store when we are talking about pipelines?
That's a right.
So what exactly are we doing here in execution of a store? Can anyone describe? So we have passed the instruction fetch stage, okay? We pass it into the register of ID execution. Now we are doing the execution stage for storing, okay? And we are sending something forward to the XMEM register before we write it back, okay? So what are the inputs here? So 1 comes from this, 2 comes from the ALU, right? And 1 comes from the other path coming after the register, okay? Can anyone describe what's going to happen here in this stage?
Is it address calculation? Like the stage is just the address calculation, right?
Where?
Like this whole stage is between like the blue bars.
So from here to here,
Yeah.
calculating address of the store.
Perhaps.
Any more ideas? All right, let me just finish with the store and then we're gonna recap them again. Okay. After passing the execution stage, now in the fourth stage, the data are written into the data memory, okay, for a store. They're coming from this XMEM register, right? And then we are trying to manipulate it in order to write it into this register. Okay. So at this point, nothing is changed for the store operation. Once data are written into the memory, there's nothing left actually to store, right? So actually, for the last stage of the store, you don't do anything. Yeah. That's why in write back, you do nothing actually. We can put all of them together instead of putting it stage by stage in one multi-cycle pipeline and showing that, okay, for load we have to do this. So it was a load x10, the address of 40x1. So you do this 5 stages, each at one cycle, cycle 1, cycle 2, cycle 3, 4, and 5, and then you have another. So this was one way to showcase this. But in order to make it easier and also in exam, we're gonna showcase it this way, right? Even without all this information, we can just write if ID X mem and WB. Okay. I'll make sure I'll post some examples next week. So after we finish the hazard, you can play around with the following the pipeline and identifying the number of stalls and bubbles it needs to have when you have a specific type of pipeline. Okay, whether or not we had forwarding, whether or not we had other type of optimizations there. Okay. Another way to showcase this was at the stage that we have add x14, x5, and 6, right? The stage that we are fetching that instruction, the one after that. So this is our hardware, right? This stage is done for that specific instruction. This portion of the hardware is being utilized to add, right? So we are actually utilizing every portion of our hardware to do one task here, okay? This is another way to showcase it. Now, we know more or less how the pipeline works, but how we control it, we still haven't discussed it. If you recall early chapter 4, we were talking about ALU Control Bits, right? that we presented in perhaps lecture 1 of chapter 4, and then how we're going to control each of those types of operations. Okay? So, looking back, you've already seen this ALU chapter 4. So this table shows how we're going to use ALU up, or those control bits, to control that. So for those that are X, we talked about this and we mentioned that these are don't care states, right? So let's see in more detail what are those 6 control signals that we are in need to access, right, to control different operations done in a pipeline. All right. So we have read write, we have ALU source, PC source, mem read, mem write, and mem to reg, which is memory to register. Okay. For the instruction fetch, we actually, what we need to do is the control signal to read, right, and write the PC are always asserted. So at this point, when we enter this phase, we don't need to assert anything else. So when we reach this state, that means that the control signals and read instructions are already okay. Okay, so we can pass through that and go to instruction ID. ID or instruction decode. At this stage, the 2 source registers are always in the same location in RISC-V. So I put all the information here, so when you pass through the slides, you can grab the overall information. And then you can always refer back to this to see which of those are getting used. After that, for execution, so we're going to execute the operation, right? So we're going to use ALU up and ALU source. These two, the signals select the type of ALU operation, and either they're going to read, right? Or just like your colleague mentioned, we're going to sign extend the input to the ALU. That was for the X stage. For the memory, the control lines in this stage are branch, mem read, and mem write. And finally, for the write back, the 2 control lines are obviously mem to reg, because we are writing memory, right, to register. Okay. Now, in order to control this, again, this is a recap of the control instructions we described early in chapter 4. Since pipelining the data, we don't change the data path, right? So whatever we had before in early chapter 4 is going to remain the same. So this table will have the same value just like before and after pipelining. Okay, I believe it was in section 4.4 when we described this. The only difference here is now you understand when we group them in stages, so the execution, memory, or write back, what are those that were asserted, okay? So, put this in blue, mapping onto the, as a pipeline control, we're going to see that these are the simplified version of the control in order to control each of those stages when we are dealing with the pipeline. Okay. In reality, what it does is at each stage, the control needs to assert this amount of operation ahead of itself. So the more you go forward, one of them has been already done, so one is going to be, so when you reach this stage, we are doing actually the X, so the X will be gone. If you reach this stage, your mem is gone, so you already, the only thing you have to do is like write back, okay? All right. Any questions so far?
Over the IF stage, how do they match? How do they find the function? How do they find the instruction? Is it based on output?
Yes. So your program counter, yeah, it's going to read each of the lines and it's going to find what instruction to fetch, and then it's going to pass it to the next line. Okay.
Okay, so and after finding the instruction, where does the PC pass the instruction?
Where?
Yes.
So you mean before this? So here. So after we finish this, the PC source we're gonna update for the next round of operations. Say either you're gonna come back after doing certain operations, going back, or you were starting right here, and then it's gonna come somewhere outside. Okay, so it's either way. It's gonna be PC plus 4, and then you're gonna go back here. Can you handle data hazard, or you're tired?
Tired.
How tired are you?
Very.
So you're always tired.
Yeah.
Get some multivitamins.